This video is on voltaic cells and a little bit of discussion of how to calculate the voltage that a voltaic cell creates. Okay, so several things we have to talk about. So we've just finished a discussion on oxidation and reduction reactions, like an intro. We've talked about oxidation numbers, how to decide who is oxidized, who's reduced. We know that oxidation and reduction reactions occur together. Okay, so now we're talking about a chemical reaction which produces a voltage. Okay, so this is a spontaneous reaction. Oops. That is capable of producing a voltage. Okay, so you think of voltage like batteries, able to power something. That's actually what this is. It's just that it's a chemical reaction. And voltaic cells are very characteristic looking. They look like this picture on your paper and in this video. So a voltaic cell, which I should have said also has another name, which is galvanic cell. So they're pretty much synonyms. They mean the same thing. A voltaic cell will always resemble this picture. So it'll be two beakers of two different solutions, okay? And then there are two pieces of metal in each of those beakers, and that's what this is, and then this here, okay? There's a device that connects the two beakers. We'll talk about that later. And then the two pieces of metal are connected with kind of like a circuit, and then there's an apparatus that can read the voltage, okay? So this is what a voltaic cell looks like. So let's talk in detail about this. So your picture is labeled much more than my picture is so far, and we'll label that as we go because I want to talk about each component before it becomes overwhelming. Okay, so we have these two pieces of metal, and our picture, let me make sure I draw it correctly. Yeah, our picture says that this is zinc metal and this is copper metal. Okay, so it's a strip of metal, and these two pieces of metal are called electrodes. And so they are solid metal. In this case, our electrodes are zinc and copper, but that's not always the case. They can be any two metals. Okay, and specifically, the two electrodes have more specific names, and they are called the anode and the cathode, and your picture is labeled. The anode is where oxidation occurs, and the cathode is where reduction occurs. The memory trick for this, remember this chapter is full of memory tricks like oil rig. The memory trick for remembering this is that anode and oxidation both start with vowels, while cathode and reduction both start with consonants. And so that's the easiest way to remember which occurs where. It's very important that you know which half reaction occurs at which electrode. So your picture is labeled. It says that zinc is the anode and that the copper is the cathode. Okay, your picture won't always be labeled, but there will be something that will indicate to you which reaction is occurring where. Might not be that they're labeled anode and cathode, and we'll see that later. Okay, so from here, now we can talk about several things. So in each beaker will contain the ion of the metal electrode. So in this beaker, we have to have a solution that contains zinc plus 2, and in this beaker, we have to have a solution that contains the copper ion in it. We're going to go with copper plus 2 in this case. So it could be anything, but it would need to be something that was soluble, that would give you a solution. So a lot of times, we use like nitrates because we know nitrates are soluble. Okay, and so this beaker would be a solution of copper nitrate, and this beaker would be a solution of zinc nitrate. Now your picture has shown it ionized, okay, and it's a little bit confusing because of the nitrate ions, but your picture is showing you that they're in there. For me, I'm gonna I'm going to not put them in my picture because what's important to us is the metal ion. So this beaker has the zinc +2 aqueous ion. This beaker has the copper +2 aqueous ion. Yes, there are nitrate ions in the beaker, but I'm not going to draw them just for simplicity reasons. Okay, that's why they're on your picture. Okay, so now I have my two solutions and I have my two electrodes, and I know which species is where. Now let's go to that we know oxidation is occurring at the anode. Okay, so we know that zinc is the anode, and oxidation has to be occurring. Well, we know that oxidation is loss of electrons. So something is losing electrons. And we have two species here. We have zinc metal and we have zinc +2. So if you think about it, there's only one way this reaction could be occurring where electrons are being lost. And so the half reaction that's occurring at the anode is that the zinc metal is losing 2 electrons and creating the aqueous zinc +2 ion. Okay, remember oxidation is losing. Loss of electrons means they're on the product side. And I know that oxidation occurs at the anode. Okay, so then at the cathode, we know reduction must be occurring. Again, we have copper +2 and we have copper. Something is gaining electrons. The only way that we can rationalize this is that it must be the copper +2 ion that gains 2 electrons and turns into copper solid. Okay, so now I have labeled the half reactions. I know where each half reaction is occurring because I know who is the anode and who is the cathode. Okay, so that's super important. All right, so from there's something else that's labeled on your voltaic cell picture, which is that right up here, they show you an arrow, with electrons. And they say this is how the electrons are flowing. And up until a minute ago, you might have said, well, how would I know which way the electrons are flowing? But step back and think about it. At the anode, this is oxidation. Oxidation is the loss of electrons. So electrons are being lost over here. They have to go somewhere. And then reduction is occurring over here, which is the gain of electrons. So it makes perfect sense that the electrons are flowing from the anode to the cathode. That will always be the case. So let's make that a bold statement. Electrons always flow from the anode to the cathode. Now, can you memorize that? I mean, you can, but I think if you, again, step back and say, okay, we know that if I can pinpoint who the anode is, I know that oxidation always occurs at the anode, which means there's always going to be electrons lost at the anode, and so they're always going to flow from the anode to the cathode. Okay, so we can learn an awful lot of information just based on the fact that we were told that this was the anode and this was the cathode. Okay, we've come up with all this information, the two half reactions, which way the electrons are flowing, where oxidation and reduction are occurring, because we know which anode was which. Okay, and then the last thing that we have yet to talk about is this U-shaped connection between the two beakers. Okay, so voltaic cells or galvanic cells are different in terms of, you'll notice that like this reaction was never completely like mixed with this reaction. You know, we think about chemistry mixing beaker A with beaker B and having a product beaker, and this is very different because these two beakers are connected via some external connection, okay, for lack of a better word, and we're not pouring like one beaker into another. So this connection, okay, right here is called a salt bridge. Oh, goodness. Okay, so this is called a salt bridge. And then I'm going to come down here and talk about the salt bridge. Okay, in fancy electrochemical cells, a salt bridge is like a U-shaped glass wire piece. Okay, so it could actually be something as simple as a piece of string or something that connects beaker 1 with beaker 2. So we'll call it, or we'll just say it connects the two beakers. And it's important because it allows movement of ions to maintain neutral solutions in the beaker. And I'll explain what I mean by that. So the salt bridge always is going to contain a chemical that is soluble that will ionize, okay, to produce a positive and a negative ion. So in your picture, your salt bridge contains sodium nitrate. Sodium nitrate is a fantastic choice for a salt bridge because think about it. If it's an aqueous solution, sodium's always soluble, nitrate's always soluble. This chemical is going to ionize and give us the Na plus ion and the NO3 minus ion. Okay, it's not your only choice for a salt bridge, but it is one that is used often because of solubility rules. Okay, so let's talk about this idea to maintain neutrality in these two solutions, because this is super important. All right, so if we go back up to my cell. Okay, I know that at the anode, oxidation is occurring. Okay, and so oxidation, and here's your reaction, is the solid zinc is creating the zinc ion. So as this reaction flows, the zinc electrode, right, is creating zinc plus 2. And remember that this zinc plus 2 originally came from here. So originally, at time 0, we had a neutral solution in this container. We had 1 zinc plus 2 and 2 NO3 minus 1s. Okay, it was neutral. But as this reaction progresses and zinc turns into zinc plus 2, we get this buildup and buildup and buildup of positive charge, right? Because all we're doing is producing more zinc plus 2. And so we need these two solutions in both beakers to remain neutral, and that's the purpose of the salt bridge. So the salt bridge, again, think about it, I've got too much positive charge in this beaker, so I need the negative ion to flow into this beaker to maintain charge balance. So that's why your salt bridge shows you that it's the nitrate ion that's going to flow into the anode beaker to cancel out the positive charge. Okay, I wouldn't memorize that. I would, again, rationalize it, think it through. Reverse, in this beaker, right, remember this is the reduction beaker, so if we want to see the reaction, here it is. The copper plus 2 is gaining 2 electrons and turning into copper solid. So at time 0, we have a neutral solution, right, 1 Cu plus 2, 2 NO3 minus 1s in this beaker. But as time progresses, the Cu plus 2 is turning into the copper. So I'm removing the positive charge from this beaker. It's getting too low. And so for that reason, your picture shows you that it's the cation from the salt bridge that's going to flow into the cathode beaker to remain or to maintain a neutral solution. Okay, that's a big question on the AP test. They love to ask that, which ion is going to flow in which beaker and why. And it's all about maintaining the charge balance during this reaction, okay, in those solutions. Again, I don't think I would memorize it. I would just use my critical thinking skills to rationalize, what beaker needs more positive and which beaker needs more negative. Okay, a couple other things to talk about before we get into the calculation of how do they know this number is to talk about actually what happens to the electrodes as this process occurs. Okay, so as this reaction is happening, remember again, at the anode, oxidation is occurring. So zinc solid is turning into zinc plus 2. Well, that means that I'm losing some of the solid zinc from this electrode. So the anode will actually have a mass decrease as this reaction occurs because the zinc is turning into zinc plus 2. And then, as you might guess, the cathode is going to have a mass increase because the copper plus 2 is turning into copper solid and depositing itself onto the electrode. So that cathode's mass will increase. For that matter, we talked about in transition metal discussion how transition metals are sometimes colored. Zinc plus 2 is not colored. However, copper plus 2 is. Copper plus 2 is blue. So this solution of copper 2 nitrate would be a vibrant, blue color. And then think about this. Think about what would happen to the color of this solution as the reaction occurs. Copper plus 2 is turning into copper solid. So we're reducing the amount of copper plus 2 in the beaker. The blue color is going to dissipate, or it's going to get lighter and lighter as this reaction continues. Now you might say, well, what about, we're continuing to put positive charge into this beaker. It should say the same. No, we're continuing to put positive charge. Yes, but it's sodium plus, right? That's not going to cause any blue color. It's not colored at all. So voltaic reactions or voltaic cells are actually kind of fascinating when you think about it. We have a gain and loss of mass on the electrons. We have electrodes. We have a flow of electrons. We might even see a color change in one of the solutions as we progress through, the reaction of this cell. Okay, one more thing before we start talking about voltage, and that is that there's a way we can write this cell. It's kind of called cell notation. And it's like a shorthand, okay? And the way to write it is to write the oxidation and then the reduction. And so again, remember, there's my half reaction. Zinc is being oxidized to zinc plus 2. So one way to do this is to say, okay, zinc's solid, and then we draw a single line going to zinc plus 2 aqueous, and this is the oxidation part. And then a double line is to indicate the salt bridge. And then we say the reduction was copper plus 2 being reduced to copper solid. So if you ever see this is just kind of like a shorthand. Oops, I should label this. This is the reduction. It's kind of a shorthand to represent this whole picture. Okay, this whole picture can be summarized with this as a cell notation, showing you that this is the oxidation reaction, half reaction that's occurring. This is the reduction half reaction that's occurring. Okay, I'm going to go ahead and stop this video here because I need to insert a photo for the discussion of voltage, and I neglected to do that. So that's a discussion of voltaic or galvanic cells that are spontaneous reactions that kind of react externally